So here's our simple circuits app. And perhaps the first thing to say is there's not very much on the screen. We're trying to keep distractions and unneeded questions from your students to a minimum. And of course, this also reduces cognitive load. So you have to build your circuits in this grid arrangement. This has two key benefits. Firstly, it means your circuits have this schematic look, so it's really clear what's connected to what. And secondly, the picture of your circuit blends nicely to the corresponding circuit diagram. You can also blend to an animation that shows the current too. So if you increase the voltage of the battery, you can see the current increasing. You can also switch to a view of moving charges. Now you can think of these blue things as electrons, and we're only showing a tiny, tiny fraction of the number that would be in a real circuit. Or you could perhaps think of each one as a coulomb's worth of electrons. Either way, a key learning point here is the charges are always in the component. So if I add a wire outside the circuit, it still contains charges that can move. They just have no net movement overall. Now if you change the voltage of the battery, you can show students how current, that's the rate at which the charges flow, changes. And if I switch that bulb for a resistor and change its resistance, we can show how resistors impede the flow of current. But there's one really important idea not shown yet, and it's the most difficult one, and that's potential. So here's how we show potential. Imagine each of those charges could show the potential of the circuit wherever it is. That's what the pink circles are. The potential is high at one end of the battery and low at the other. And the circuit loses this potential as the charges make their way around. Now there are lots of analogies to explain voltage, using things like height or trains or water pressure. But with this approach we can help students visualise the potential in the actual circuit, rather than expecting them to make the leap of imagining their circuit as something else. And now we think you can introduce the idea of potential more mathematically. Potential is the amount of energy per unit charge. V equals E over Q. So for each of those charges, there's a certain amount of energy, E, which gets given out as the current flows through the bulb as heat and light. This is shown as the emanating pink circles. And again, if I increase the battery voltage, the potential on one side of the circuit increases, and the rate of energy coming out of the bulb increases. And here's another really strong advantage of this approach. Because your students can see the potential either side of the resistor, you can explain what we mean by a potential difference. A voltmeter has to go across a component because it measures the difference in potential between 2 points in the circuit, whereas an ammeter has to go in the circuit because it measures the flow of electrons. Now let's have a look at a simple series circuit. And now you can see once again the potential difference between the two sides of the battery. But now you can also see the potential drops partly across each resistor. And now I'll turn this into a parallel circuit. Now you can see perhaps the most powerful reason to use this approach to teaching circuits. You can show students that potential at the start of each branch of the circuit is the same. And if you decrease the resistance in one branch, the potential drop across the resistor stays the same, but the current increases. And you can show the current here, plus the current here, has to equal the current here. And even better, if you look at this resistor, it should be easier to explain how P equals V times I. The amount of energy being given out by the resistor is the amount of energy per unit charge, V, times the rate at which the charges flow, I. And there's one final really big advantage to using this approach to teaching circuits. Here's a new circuit with a power supply instead of a battery. If I now switch from DC to AC, you can show how the potential changes in an AC circuit. And if you increase the voltage, you can see the small backwards and forwards flow of the current more clearly. But of course, AC has a higher rate of oscillation than this, and we can show this as well. We call this approach the See the Potential approach. And to sum up, students can see the potential in the circuit rather than having to compare a circuit to something analogous that looks completely different. You give them clear ways to visualise current, resistance, and potential. It explains series circuits well. and it explains the tricky idea of parallel circuits really well. It has the V equals E over Q mathematical foundation at its heart. It shows P equals V times I really well. It works really well for AC as well as DC. Most importantly, your students have to get to grips with just one visualization to help them understand all these concepts. Thanks for listening. The Simple Circuits app is available as a standalone app for iPad or Android, or also as part of Sunflower for Science for school subscribers.